Hello, class. Good afternoon. Let's get started. So today is Tuesday, so we will begin our class by solving this attendance quiz. Today I prepared about 9 quiz problems, but in my opinion, the problems are not difficult, so you can easily solve them. I'll give you 10 minutes. Yeah. Oh, my bad. today's problems are easy, right? So I don't think we don't have to solve them together. For your information, you can find some 4 months free trial for Gemini Pro online. So if you have finished your quiz problem, you can search them online. Or you can search the links for the free 4 months Gemini Pro trial after this class. After this class, I also share my referral links to get the 4 months Gemini Pro trial. Okay, time's up. Do you have any questions about for the today's quiz? Not really. Okay, then let's start the lecture. So from the previous class, I got one question for the survey. Are linkers, loaders, compilers, and similar tools also components of the OS? The simple answer is yes, they are included in the OS in a broad sense. In Korean, 넓은 의미로. So they can be considered a part of system software or program of an OS. Especially linkers and compilers or some etc. They will be considered as a part of the system software and program. And definitely loaders are included in the OS kernel because the loaders lore is loading executable program into the memory. So loading the program and preparing the memory is more closely related to the corner things. So, and not even in a broad sense, loaders are included in the OS parts. Okay. From last class, we missed some slides, right? So let's go back to the previous lecture slide. From the previous lecture, we covered many things, and lastly, we have covered the corner modules and 4 components to support them. So we have these things. Yeah, we ended up at here. And the remaining things are some examples to build and use the custom corners. And I prepared some live demonstration to do this. So we were gonna see these things again. So, so from last class, we have studied about the Linux system architecture. So we have user space and kernel space. So we have some user program and some libraries in user space, and we have some system cores, device drivers, and some kernel things in kernel space. Yeah, not important. So from now on, we are gonna study 5 core functions of Linux: process management, memory management, file system management, I/O management, and network management. From today, we are gonna study about the input, output, or device driver management. And before studying the I/O things, let's take a closer look at this example. So through this example, we will build a kernel module, and we will try to load the built kernel and unload the kernel. So let's see this code together. So yeah, here's the guidelines. Yeah, so we're gonna create a hello.c and make file to make a kernel file and build it. So this hello.c defines the kernel module and its initialization and cleanup functions. So when this kernel is loaded to the kernel, so it will, when the module is initialized, that this function will be called hello init. It simply print the hello world to the kernel. And when the kernel is unloaded, then this module exit will call this hello cleanup function. And then it will simply print out this string cleaning up module. That is what our custom kernel does. It's very simple, right? And this make file, we're gonna compile this hello.c file in the current directory and build the kernel module. So to follow this example, you cannot use the WSL on the Windows subsystem for Linux. You cannot use this because in WSL2, the kernel is Microsoft provided kernel, which is not the same thing as anticipated from this kernel. So we have to use the Linux kernel, but it is not the exactly same thing. So you cannot use the WSL for this example. Also, recently our TA uploaded some LKEM materials, right? So if you see this link, that this document will say that you cannot use the WSL for this tutorial, and this PDF means that our third assignment is coming. So the assignment 3 will be posted soon. So you can follow these tutorials to have some hands-on experience on loadable kernel modules. And okay, so you cannot use the WSL for the kernel programming. So you have to use native Linux machine, or you have to install a virtual machine. You have to use the virtual machine to use the native Linux operating system. So for Windows users, there are many options. You can use VMware, or you can use VirtualBox. Personally, I prefer VMware than VirtualBox, and because in my experience, the stability of the VMware is way better than that of the VirtualBox. So I recommend to use the VMware. But it is little bit annoying to install the VMware because you have to register on an account on the Broadcom website. So, but I think it is worth it. So, but anyway, it's your choice to choose the virtual machine. So to follow this example, you have to use the native Linux or virtual machine, or use the virtual machine. And let's see the hello.c code. So we have some headers. It's not familiar, right? But they are just headers. So let's skip the details about these things, and let's see the next part. So we can see the capital module, blah blah blah. So this capital module macros describe module data. So you can specify its license, author, and also you can describe some simple things about this kernel. And you can see some static functions and the print k function. So it's very similar to the printf. It will just print some message to the kernel log. So this message will be printed on the kernel log, not on the standard output. So we cannot directly see this message from our terminal. Okay, and we also have some small letter module macros, which will call some functions when the modules are loaded or unloaded. That's all for the hello.c file. And let's see this make file code. So its role is to simply compile the hello.c file. So you can see some options. So we have hyphen large capital C option, which moves the build kernel to the specified directly, and we also have these options that specify the absolute path of the module directory. Yeah, it's not actually they are not important. And let's see this $shell uname hyphen r. So if you haven't taken the missing semester from after which was solved after the midterm exam, I guess you are not familiar with this dollar symbol. So let me explain. So if you type this uname hyphen r, then it will print out the version of the current running Linux kernel. And this shell means let this terminal to the type the uname r to the shell. And this dollar symbol means that dollar and shell uname hyphen r means that run this command to the terminal and put the result to the here. So this thing will print out some version of the Linux kernel, right? Let's say the version name is ABC. Then finally, this line will be treated as like this: lim modules ABC build blah blah blah. Yeah, that's how this dollar symbol works. Okay, then I think I explained all the details of the make files and hello.c. Then let's take a look of the live demonstration. Okay, so yesterday I installed Linux on this virtual machine, and I have already written the hello.c and make file on this system. So we have hello.c and make file right here. So to build the kernel module, we have to just type make and enter. Then this command will build the whole things. So we can get this KO file, the kernel object file, and we can load this kernel module, kernel object, by type the insert module hello.ko. However, you have to type sudo at the head of this command. So this command will load the hello.ko object to the current operating system. By the way, from the hello.c file, we have seen that when the module is initialized, this kernel module will call the hello init, which calls the print_k function and print out hello world. But even if we loaded this kernel object, we cannot see this hello world message, because this message will be printed on the kernel log. So currently we are seeing standard output, right? So we cannot see this message. So to see the message, we have to see the kernel log, and this instruction will show the kernel log. So there are many messages, and we can see this hello world. It means that our custom kernel is loaded to the operating system successfully. And we can unload the kernel by typing sudo remove module hello.ko. So this instruction will unload our custom kernel, and also we can see the we have to use the sudo in front of this command. Not sumo, sudo. Yeah, so we can see this message, which means that the module is cleaned up from the operating system. And from if you see the provided material, that you can see the command like this. So this tail -1 means just show the last one line from the D message. So if we type this thing, it will just print out the last line, these things, this one. Yeah. And also from the hello C code, we have seen that we included some metadata for this kernel. To see the kernel module's metadata, we can type mode info and the hello.ko to see the author of this kernel module and its license. Yeah, so all the metadata can be seen through this mode info instruction. Okay, that's all for the live demonstration. Do you have any questions? It's very easy, right? So I hope the assignment 3 is easy as this one, but I don't think so. It will be much way different than difficult than these things. Okay, that's all for the live demonstration. Okay, then let's start today's topic, input-output systems and its operations. So today and next time, we will cover an overview of I/O subsystem and their operations. So today we're gonna learn about stream model, I/O functions, buffering, and next class we will learn about pipes, file and device I/Os. So among the 5 core functions of Linux, today we will cover the fourth one. For the reference, you can see this. You can refer these textbooks. Yeah, we have seen this picture before, right? The overview of operating system, and so a view. So today we will cover this I/O operations. So I/O means input and output. So I/O is a process of copying data between main memory and I/O devices. So at here, I can give some examples of the I/O devices: disk drives, keyboard, mouse, terminals, and networks or displays. So in this I/O subsystems, we will focus in this subsystem. We means main memory. So input operation means copying or moving data from I/O devices, and output operation means moving data from main memory to the I/O device. And there are several different I/O operations. Firstly, we have user I/O. It means interaction between program and a user, typically through a keyboard and display. And we also have file I/O and device I/O, which mean interactions between a program and the file storage or some peripheral components or sensors. So to support the I/O operations in the operating system, we have to do some laws. We have operating system have to do some things. So the first law of the operating system is I/O device control. So I/O devices vary so widely in their function and speed. So we have many I/O devices, and their functions or speed will be very varied. So varied method to control them is not, so we cannot have one single control method to cover all the I/O devices. So to cover them, so this method form the I/O subsystem of the OS kernel. So it will separate the rest of kernel from the I/O device management. So to handle them, we will use the device driver, which is a which can by serving a uniform device access interface to the I/O devices and I/O subsystems. Many system cores will provide a standard interface between the application and the OS, or the OS and the devices. So OS can have the device driver for each device controller through this uniform access interface. So by using this structure, we can encapsulate and the details and some varied functionalities of different devices. By using this device driver modules. And the second law of the operating system is I/O operation management. So I/O operations or I/O transactions occur when a program receives bytes from a source or sends bytes to the destination. So to support this I/O operations, modern operating system support the stream models. And now let's see what the stream model is. So any I/O transactions or operations can be viewed as a flow of byte stream. So here stream means like a small lever. So from a source to destination. So to the programmer, stream is a pointer to pointing out the source or the destination, where the byte flow ends or starts. So the OS creates and manages the streams based on some function calls like open or close. And this high-level standard I/O functions will be contained in some libraries. So let's see an example to use the stream. I think these examples are very simple and easy because most of you have already tried this from your C programming classes. So let's see. So this command fopen will open this file, and it will create a stream connection between the program and a file. So this line will open this stream, and this stream printf will use this stream and passes bytes along this stream. So you can send this string to the output file, and after the byte transaction, we have to close this file, and this fclose will eliminate this generated stream. So when the stream is created, we can think of it as having an address from which bytes are sent and an address at which bytes will be received. So, and all these addresses will be controlled by the operating system. Yeah, we have already studied about this thing on your first grade, right? And there are several functions to use these streams. So familiar ones are fprintf and fscanf functions, which are specialized to handle the formatted text data. So you can use %s or %d when you use the fprintf and fscanf. And the general function for this purpose are fread and fwrite, and they cannot use this %s and %d because they only can send the raw byte, so you cannot use this the formatting things. So at the heart of fprintf and fscanf, there are some lower level buffer I/O operations like fread or read or write, and actually there are many ways to implement the fprintf or other functions like fscanf or fread or read, and it depends on their implementation. So some fread, sorry, my bad. Okay. Some some implementation of fprintf will use this fread or read to implement this function, but some of other implementation will not use this read or fread to implement this fprintf. So it depends on the C library. So there are many ways to implement the fprintf, and I prepare some links to see them. So if you go to this link, then you can check how the fprintf or some other functions are implemented. Then let's see how fprintf and fscanf works. So fprintf, when you use the fprintf, bytes are being sent down to a stream. So let's see this code. So to use the stream, we have to generate the stream. So this line will generates a stream. The name of the stream is fpt, and this fprintf uses this stream to send this string to this file. And yeah, it's very easy, right? But you have to be careful to see this. So in the memory space, we have to put this null character to specify the end of the string, right? But in the file system, in the disk storage, you don't have to put null to the null character in the last of the string. So after using this fprintf, the first byte will store anything. So it is empty. That's the one huge difference between the memory space and the file system. And for your information, so this sentence talks about the 42 bytes, but actually the size of this string is 40 bytes. So don't be confused. Okay, then and also at here, one character means 1 byte. Just for your information. Yeah, that's all for the fprintf. It is not difficult, right? It's very easy. And let's see fscanf. So it will be used to read some string from or data or bytes from the file to the main memory. So let's assume that the data.txt saves this string. So firstly, we have to declare a stream to use this fscanf. So firstly, when you use app_open function, this pointer will point out the beginning of the file. So it will point out the first byte. And if we use the fscanf, it will try to read 8 bytes because we specified this %s format specifier, fscanf read the characters until it encounters new line or white space. So here is a white space. So this fscanf will try to read all these characters, and when it encounters white space, it stops reading. So after the reading, this file pointer, the fpt, will point out the 9th byte, and this 8 bytes will be copied to the main memory. And also at here you can see that this is the the value of this 8th byte was 32. However, because we are handling strings in the main memory, we have to specify null character, the value 0, at the end of this string. So that is one more other differences between the main memory and file system. Okay, that's all for the fprintf and fscanf. And we also have a lower level I/O functions, fread and fwrite. So their roles are very similar to the fscanf and fprintf. So fread will read the data from the location, and fwrite will write down some element to the given pointer, given string. So the fread and fwrite reads and writes the raw bytes between memory and stream. However, fprintf and fscanf supports so formatted I/O things, so you can use this %d or other things to when you use the fprintf and fscanf. Also, their how can I say it? Their types are also different. So you can use size t for the fread, fwrite. So you can use you can change the size of your function call. However, fprintf and fscanf, their types are integers because the difference is due to their return values. So on success, fread and fwrite return the number of items read or number of items written. Yeah. So if you have read 7 items, then this fread will return value 7. Yeah. So if you to read or write the huge numbers of data, you have to change this size t, like long or other things, and that's why we have different types for among the fread, fwrite, and fprintf and fscanf. I also prepared synopsis, description, and return value for the fprintf and fscanf at the end of this material, so you can check by yourself. So let's see an example of fread. So it will read some byte from a source. So to use this function, we also have to make a stream, and we have to use fread with 4 parameters. So firstly, we have to specify destination address, and we have to specify size per element and number of elements. And the last parameter will specifies the input stream. And as I told you before, fread does not support some formatted things. So at the end of string, we have to add this 0 value separately. And because we have we are trying to read only 15 bytes, so the output will end that here. Yeah. it is not difficult, right? And as for the F write, it will move the bytes from program into the destination, like a disk. So the parameters are identical to those in freed function. And here's an example code. And so we have to also make a stream to use this fwrite function. And at here, we can see another function is located at here. So this fprintf is just storing string into the destination. So this sentence, this string will be stored in the text variable. And this strlen will count the length of the characters. So the value of strlen text is 40 because we have 40 characters in this string. Yeah, it's not difficult, right? Then here's a short question. What do you expect from here? So guess the output of when we run this code. Let's say this data.txt stores this one, this string. So what is the answer? 40, 42, 70, or 80? The answer is 40. So the size of this variable is 80. And this fread function will try to read 70 bytes. However, the size of this file is 40 bytes, right? So as I told you before, fread will return the how many elements are read or written. So this function will read 40 bytes, and this function will return 40. So the answer was 40. It is clear, right? Okay. So we also have some other functions like open, close, read, write, named as system calls. However, they are very similar to the fopen or fread, so I'm gonna skip their explanations. And so they may behave differently depending on which OS are called from. So, however, standardized C library therefore expected some behave similarly regardless of the operating system. So it is not much important. So we have standard I/O streams. So you begin your C programming life by using this standard input-output header, right? So they support these 3 streams. So we have standard input, standard output, and standard error. So standard input connects keyboard to the program, and output connects program to display. I guess you are familiar with the standard input and output, but I guess you are not familiar with the standard error. So it's a backup output stream for programmers. So we usually use this standard error to print out some errors. And there is a difference between standard output and standard error. So standard out is line buffered and standard error is unbuffered. So we will learn about this buffering means shortly. So you're familiar with scanf and printf, right? So scanf can receive bytes from any stream. However, scanf is hardwired, so their stream is fixed to the standard input or standard output. So that's the only difference. So if we use fscanf and use the standard input as a stream, this scanf and fscanf will behave identically. So yeah, that's all for this slide. And here is a buffering. So from the SIG example, we have seen this buffer, right? We had input device and output device, and we also had a buffer. So buffer is a temporary storage between sender and receiver of a bytes of stream. So it's an additional piece of memory that it is used to moderate the flow of bytes. So buffering is done for several reasons. So what if the sender puts bytes into the stream faster than the receiver can handle? So let's say we have a very fast CPU and we have very slow disk drive, and CPU sends a lot of data to the slow disk drive. Then because the speed of the disk drive is very slow, they can save all the data to the disk driver. So in this situation, a buffer can store the extra bytes temporarily. So we can save all the data to the buffer at first, and we can slowly move the data to the slow device, slow disk drive. And also, what if a program is in the middle of calculation and not prepared to receive bytes? So let's say a CPU is very busy and disk driver wants to send the data. So in this situation, a buffer can keep this data until the device is ready. So that's why we have to that's how the buffer can cope with the device speed mismatch. And also the buffer can cope with device data transfer size mismatch. So it is very common in networking. So let's say a device wants to send some data per 4 bytes, and receiver wants to take data per 1 byte. So this situation is the data transfer size mismatch. So in this situation, a buffer can collect this data and can split these 4 bytes into the 1 byte and send them successively. Yeah, that's how the buffer works. And also, buffer can be used to preserve the intended works. So let's say user buffer stores hello, and we want to move this string hello to the disk. If we use the buffer, the value of this user buffer will be copied to the kernel buffer, and then this kernel buffer value, the hello, will be stored into the disk. And let's say during this example, a user modifies its buffer from hello to by. When we called this write function at here, our intention was copying hello, this string hello, to the disk. However, during the copying process, the user modified its buffer value. So if we don't have the buffer, then this string by can be stored into the hello, to the disk. So that's why buffer can guarantee the intended operation in the operating system. And to use the buffer, there are 3 types of buffering. So it's based on how the temporary storage, the buffer is flushed. And at here, flush means moving the forcing buffer data to be sent from the buffer to its final destination. So if you have some data in the buffer, and if you try to flush them, you will remove all this data, and you will move this data to the final destination. And we have 3 types of buffering. The first one is block buffering. So the buffer is flushed when it receives a certain amount of data, like 1 kilobyte or 16 kilobyte. It is commonly used for the large data transfer. And we also have line buffering. So the buffer is flushed when it receives a new line character. So standard output uses this line buffering. And so the last type of the buffering is unbuffered. So buffer acts as we don't have a buffer. So when we receive any bytes, then the buffer will be flushed. So standard error is using this unbuffered buffering type. Also, the type of buffering on stream can be changed through these functions. And we will have a look of an example of this line buffering. So I prepared 3 C code. So let's read this together. So we have a for loop, and it will print out 5 lines. The difference between this one and this one is just a new line character. And the third example, we add this manual flush to the first example. So and after printing out one thing, we will sleep for a second. So let's see the first 2 examples. So like this. As I told you before, the standard output uses the line buffered things. Line buffered. So because we encounter this new line every 1 second, we can see the result every 1 second. However, we don't have new line character at here. So after 5 seconds, we can see the printed result after the 5 seconds. Yeah. So our result will printed at once after 5 seconds. And also, in the third example, so because we manually added this F flush, so every 1 second the output will be printed. Okay, so yeah, that was the buffering. And the earlier class was ended at here, so we will stop at here. Do you have any questions for today's class? Okay, then that's all for today. Before ending end of our class, let's take a survey. Okay, I explain this thing next class. Because for loading the module or unloading the module, we need some privilege. But just seeing or observing the corner module, we don't have to use the sudo. Yeah, that's the reason for this comment. Okay, that's all for today. See you next time.